So which one do you want me to go through or explain?
Part 4, problem J, I think. Yeah, J.
So asking for VL. So what's the overall voltage drop? Yeah, 200 volts. And what's the overall resistance? 20K. So you can use 200 volts divided by 20K to get a current. And so what is a current though, in this case? I draw it here. So it will be I equals to 200 volts over 20K ohms, which is 10 what? Milliamps, million, not mega, million, right? 10 to the negative 3. And so that's the current flow from here to here, like clockwise in the circuit. So in that case, when it flows through the first resistor, here's grounded, 0 volts. Oh no, here's grounded. Here's not. What's the current here? Yeah, 10 milliamps. So you'll know the voltage drop instantly, right? So you can get a voltage drop instantly. And that will be 100 volts. It's 100 volts difference. It's a potential difference from here to here. From here to here is a potential difference. And you got a 10 milliamps here as well, and the resistance is 10K. So the potential drop across this resistor will be 100 volts as well. And total you have 200 volts. 100 here, 100 here. So you're wondering what's the voltage at this point. Remember, all the voltages are kind of relative. That's why when we are talking about the voltage drops across the resistors, we have to say it's being dropped from where to where, right? This guy, this 100 volts is being dropped from here to here. That's a regular way we talk about the voltage. But sometimes we also want to say, I can also say like the voltage at this point, because this point is being labeled as V out in the circuit. If I'm just saying like the voltage at this point, I'm comparing the voltage here to the ground, which is here. And that is the voltage drop from here to here, or it's the same voltage. I just say it's a node voltage of this point, which is V out. It's a node voltage. So here's a question: what's the node voltage here, or what is V out? How to calculate it? We only know the voltage dropped across this resistor is 100 volts. But what's the voltage at this point? You have to start from somewhere, right? So what's the voltage at this point? No, the voltage at this 2 point. I'm comparing to where? The ground. So starting from the ground, and it's being incremented by 100 volts. So the voltage at this node is 100 volts compared to where? The ground. So here's 100 volts, dropped by 100 volts. So what's the voltage here? It's 0. Sounds odd, right? It's not being shorted to the ground, but it's 0 volts. You know what's happening?
And then it gets dropped again.
Yeah, so 0, yeah, here's negative 100 compared to the ground, which makes sense because the voltage source is going to force the voltage to be dropped by 100 volts from here to here. That's designed by the engineers in the company, right? If it's designed as 100 volts from here to here, then it should be. Let's see if there's anything else we can think about this circuit. You must be thinking that is there anything wrong with this circuit? I don't think so. No, it's just simply 0 volts. Mm-hmm.
Yeah.
And this one is a switch. By looking at it now, it's an opened switch, so it's not closed. So which means it's disconnected from here. I won't take points from this problem though. I mean, so what's the voltage at VL2? It's not 0, it's not grounded. Is it 0? It's just nothing. I mean, I didn't teach that last time, so I won't take points off. You won't say, if I just directly grab a wire, it's a floating wire, like this one, right? I just grab it. Can you just say like the voltage here is 0 volts? No, I cannot, because it's not 0 volts. It's just nothing. It can be a little bit of static charges, accumulated on the wire. But if you measure it, definitely it's going to be very close to 0. Probably you couldn't even detect the difference between this and 0, right? It can be like microvolts difference. When I'm holding it, I definitely have static charges on my finger, and it's going to be accumulated on the wire, like in a microvolts level, tiny. But you cannot say 0 because it's not 0. It's not grounded. Okay? It's just floating wire. It's nothing. The answer is just nothing. It's not. You don't want to say 0 volts. And so this one, we talked about it last time. They have same potential, so no current flow. It's like 2 pumps has the same pressure, pumping water to the 2 directions, so the water won't flow because it has the same pressure. What about this one? It's very similar, right? So you'll have 4 volts overall voltage drop across the circuit, and 8K as the overall resistance. So calculate the current first, and then calculate the voltage drop across each resistor. And starting from this point, since you know this point, what's the voltage at this point, V1? It's 2 volts compared to the ground is 2 volts. And 2 volts is being dropped by something to get VL. And then you are done. So for the quiz today, I think it's very similar to these ones as well. Yeah, very similar. And if I just directly draw the circuit like this, so what's happening to these points? These 2 points? They are both 0 volts. They are shorted together, right? You can directly just draw a line to connect them together. Any other questions to anything before we do that quiz? No? Should we? 30 minutes is too long, I guess. So 20 minutes, what about that? Yeah. So there's a new homework 2 due next Monday. I'm going to cover, so all the examples being introduced in this lecture will be very similar to these questions. 100 points and pretty fundamental and useful as well. Okay. So the purpose for me to introduce basic voltage and currents and also digital signals is because if you guys have a chance, maybe next summer, you want to work in my lab, so you have this basic knowledge to get started. So the voltage and currents are from circuit 1, it's engineering 201, and the digital logic is from CE 241, and both of them are the second year college classes, and they are important critical prerequisites for a lot of other upper level classes. Can directly get you a job if you work on these projects seriously. So for example, one of my students was trained in microcontrollers and fabricated 2 PCB boards and was very familiar with microcontroller design flow, starting from the power supply to programming. And he was not even a top 1, top 2 student, but he's still got a job in some tracks in Durango, which the company I told you guys if I did last time, making all these sound effects, digital modules, selling 2,000 PCB boards a week. That company, you know. So it's good to know this good stuff, right? So you can get started sooner. So first, we want to understand the numbers. So last time I gave you some examples on 0 and 1s, all these things. But the number system is definitely not just limited to decimal and binary numbers, but also octal and hexadecimal. But between these numbers, if you do not have a method to do the calculation, it's very difficult to convert in between different number systems. For example, if I write down a number like 1011, it's not very bad. It's not too bad. You can still convert it into a decimal number if this is a 2-based, which is a binary number. So what is a decimal number, corresponding decimal number of this guy? Because we know this one represent A, and that one represent 2, and that one is 1. So it's 11. Okay. So what if it becomes a bit difficult to tell directly? But can still handwrite all the numbers for every single digit. So for this one is 8 because after this digit, it has 3 bits. So which means this 8 is actually 2 to the third, and this 3 represent how many bits you have following this digit. So the same principle here. So what about this guy? It's 2 to the what? Yeah. It's 1, 2, 3, 4, 5. And what is that? 32 plus what? What is this? Yeah. I still can calculate it. 40, 47. And if I write down 47 10-based, what's the binary number? This. How to calculate it?
The lowest factor, go with the highest factor. That fits into it. So you start with 32.
Oh, you'll start with 32. Yeah, that's a good way to do it. Yeah, yeah, yeah. But when you have a larger number, sometimes it's difficult to tell. If I write down like 525 or something like that. 256 or 512, right? You can still do 512. Okay. So, but here's another way to do that. Can guarantee you can get the right answer. 47, you divide by 2 if this is division sign operator. Just in, we're assuming that's a divider, right? It's divided by 2. So what's the result? What's the remainder? 23. Is that 1? Remainder is 1, right? Because 2 times 23 is 46, and get 1 left. And divide by 2 again, the 11. And divide by 2 again, the 5. Divide by 2 again. Divide by 2 again. 1, 0, because nothing left. 2 divided by 2 is 1, and nothing left, right? And divide by 2 again. What's the result? What's the remainder? Huh? So what's the result though? 1 divided by 2. Do we have enough 2 in that 1? I want to split that 1 to several 2s. At $1, I want to get several $2. It's impossible, right? So 1 divided by 2 is what? What's the result though? 0. And I just look backwards, and it's going to be the binary number. That magic. 1 0 1 1 1 1. 1 0 1 1 1 1, right? And why? Why that works? It works. Must be a reason for that. Yeah. So you're doing by 2, dividing by 2. So what's actually happening to the number? Yes. How that works? Let's look at that. So 47 is what? We all know that right now, right? So what is that number? 1 0 1 1 1 1. If I write down this number here, is that 47? Yes. Just different form. And let's do it. I divide this number by 2. It's the same as this guy. No difference. 47 divided by 2, it's a binary form, 47 divided by 2, what I'm getting, and what's the remainder. So before we do that, let's think about this number. 2021 divided by 10, what's going to happen? So this is very interesting, right? So for decimal numbers, you divide by 10, what's actually happening to the number? Yes. To where? Yes. To the left. So you divide this number by 10, you are getting, because you move the decimal number to the left. So you are getting 202. Remainder is 1. Do it again. 22. Do it again. 2. 0. Do it again. Oh, sorry. Making sense? That's how that works. You divide by 10 for decimals, divide by 10, you move the digit to the left, and you get a remainder, which is exactly that number, right? And every number following that procedure will be all the number at every single digit. So that's why you look backwards, you can recover that number. Same concept here. The only difference is if the decimal number, you want to move the digit, you need to divide by 10. For a binary number, you want to move the digit, you need to divide it by 2. So for this number, it's a binary number. I divide by 2, what I'm getting? Whatever here, right? Whatever here. That making sense? You divide by 2, you move the binary point to the left for 1 digit. What's the result? What's the remainder? Wait, 1 0 divided by 2. So what is 1 0? 2. So 1 0 divided by 2, what's the result? 1. And also, if you just move the digit, it used to be here at the very beginning, move it to here, and you're getting 1, remainder is 0, and then do it again. Is there a difference of this one and this one? Is there a difference? No, 1 is always 1. In binary, $1 is $1. In binary, also in decimal, it's also $1. Won't be like $10. So just looking backwards, it's still the same number, you can recover it. So that's how you can convert what to what? Decimal to binary. So this thing here is for decimal to binary. So do you know how to convert binary to decimal? How and where? And did we do that? Have we done that? Binary to decimal. Yeah. But there are also other number systems like octal and hexadecimal. How to do this one? For example, a hex number. Hex. What's a hex number? to 16, right? Until 16. So after 9, we don't have other symbols to represent these numbers. So we use A, B, C, D, E, F. So what is 10? Yeah, what is F? 15. You don't have 16 because 16 numbers starting from 0. So the largest will be 15. What is E? 14. D, 13. 12. It's just biting back and forth, right? 12. Yeah.
Oh, wait.
C. Yeah. So we use combinations of binary numbers to represent hex numbers. Usually in computer systems, we are programming, we are writing a code to control a robot for a microcontroller. But it's going to be four bits of binary numbers. For example, F. So what are the 4 bits? So what is the 4 binary bits of this number? It's a hex number. It's 15. The way is, I mean, there's a way, easier way to calculate it. For example, we know that 2 to the 4th is 16. So which means if I have 4 trailing zeros, so this digit represents 16. And if I minus 1, like 1, 0, 0, 0, minus 1, what I'm getting? 0, 1, 1, 1, 1. So that's why this is 15. If you only have 4 spots, what's the largest number you can get? 15, because if I fill them up with 1s, then that's the largest number. I don't have 2s in binary, so it's going to be 15. And in hexadecimal, so the largest number is 15, so that's why 4 digits of binary spots will be enough to represent all these hex numbers. So E will be 1, 1, 0, just minus 1, right? So if I'm asking you to convert hex numbers into binary numbers, I write down a hex number A, B, C as a hex number, and I'm asking you to convert this number into a binary number. So the way to do that is just expand every single one to 4 digits of binary numbers. So what is A? 10, and it's going to be A plus 2, right? So A plus 2 means you need an A here, 4 bits, 4 digits. So the first one has to be 1, so you can get an 8. And that's 4, you don't need a 4 because 8 plus 4 will be 12. And you need a 2 here, so that's 10. So B is 11. You just add 1 to this number, 1, 0, 1, 1. C will be 12, 1, 1, 0, 0. So it's 8 plus 4. And that's it. It just directly write down the entire thing here, and that will be this number. How do you verify it? So when you're comparing these two numbers, you don't know which is which. You have to convert them into one number you are familiar with, so you know what are they. Decimal, right? So how to convert this one into decimal? It's 8 times what? Wait, let me confuse you a little bit. So this number is a hex number, right? So it's 16 based. It's 16 based. So I should write down 16 times, is that right? A to the power of 3, is that correct? How should I do it though? Or A times 16 to the second power, is that right? Or third power? So which is correct? Second power is correct. So do you want to put the power on the 16 or on A? So if you look at this one, did I put a power on 2 or did I put a power on 1? Same concept, right? So these 1010s are like ABCs. So 16 is 2 here. So it should be on 2 here and 16 here. And because I only have 2 digits trailing this A, so it should be second power. So the reason for that is if I write down a number like 2021, this 2 is not 2, it's 2000. So it's 2 times 10 to the third power. Same concept. A is not A, it's not 10, it's not 10. It's being written on the third place from the right. So it's not 10 anymore. So what is that?
Square.
It's 10 times 16 squared. Like this one, same. 2 times 10 to the third. Right? Or plus B times what? 16 plus C times. So that's the result. Just add it. Let's see. What's the result? So what's 16's power? What's 16 squared? The 196? $256? Yeah, 256 times 10. 11 times this guy. 176. Plus 12 times this one. Huh? Is that 12? Oh, times 1. Sorry, times 1. Is that 1? Yeah. So that is 2, 7, 3, 6 plus 12. Is that right? Yeah, that's right. 2, 7, 4, 8. All right, so what about this guy though? I'll pick up one to calculate it for me. I'm joking. I'm gonna use a computer though. I think there's a calculator. So you can choose programmer, and now you understand what are they, right? Bin. That's a bin there, right? Chat bin. So you know it's a binary, and you know octal, 8-based, and you know decimal and hex, 16-based. So if I choose binary, I can just type this number in there. It's 1 0 1 0 1 0 1, 1, 1, 1, 0, 0. So look at the decimal version. 2748. Woo! 2748. That makes sense? That's how you convert what to what. So this is, so you are able to convert what to what. So what did we do here? Yeah, hex to decimal is this part, right? What about this? So what did we do at the very beginning? So we convert from here to here, right? Remember, we just hex to binary. So we expand every hex digit into 4 bits of binary numbers, and we form this binary number, and it's exactly the same as a hex number. So hex to binary, hex to decimal. So what about binary to hex? After we do this, we'll have a 5-minute break. What about that? I think 10 minutes is a bit too long. Binary to hex. 1, 0, 1, 1, 0, 1, 1, 1, 1, 1, 0, 1, whatever. 1. Convert this guy to hex.
Break it up into.
Yeah, let's do it. Starting from where? Left, right, middle. It matters. Why left to right? Let's try it. 4, 4, 4. Yeah, that's right. 4, 4, 4, 0, 0, 0, 4. Just make it up. Adding zeros in the front is not changing the number, right? It's the same as 20, 21, put a 0 in the front, it's not changing the number. 0, 0, 1 is still 1. Same here. So, what is this? 1, 0, 1, 1, what is that? 8 plus 3, 11. What is 11? B. This. 1, 1, 1, 1. F. 0, 1, 1, 0. What is that number? 4 plus 2. What's 6 in hex? Still 6. 0, 0, 0, 1. 1. That's a hex number for this binary number. So now we know how to convert binary to hex. All right, let's break for 5 minutes. I'm going to cover more number conversions after that. All right, ready to get started? So binary to hex, hex to binary, hex to decimal. What about decimal to hex? How do we do that? Remember, hex to binary. No, decimal to hex, right? Decimal to binary is like this. So you can imagine that decimal to hex is going to be similar. if you want to convert decimal to something, like this one, since you don't know what are these digits, and during this operation, since we know what are they, so we can visualize that every single digit is being taken out to recover that number. But for here, we just couldn't see it if it's a decimal number. So you have to divide it by 2 every single time to find out all the 1 zeros. If the decimal number 256 or something, so what's the hex number accordingly? By 16. So what's the result? You need a little calculator. It's 256 divided by 16. It's, wait, oh, 16. It's a bad example though. Let's make it bigger. What is that? 2567 divided by 16. So how to deal with that? So divide this number by 16, you are getting 160 of these guys. The remainder is like 0.4. Huh?
Isn't the remainder 7?
So the way, but I mean, when you are doing a calculation, how do you do it? And for everyone. So you only have you have a calculator, right? So to the calculation, you find out, hey, 160. Good. So I put 160 here. And then you times this number and do a subtraction, right? Like you can directly find out it's 7. Did you get that? So this divided by 16, you got 160. And then you calculate for 16 times 160. You're getting 2560. And subtract from here, the remainder is 7. See how that works? And then do it again. 10 and 0. Right? And do it again. 0 and 10. Yeah. I just have a trap for you, but you just didn't jump into it. 807. Is that right? Good. So now you know how to convert a decimal number to a hex number. If I ask you to convert a decimal number to an octal number, you can still do that. Octal, 8-based. Or I just let you know, like, there's a number, it's a 3-based, right? Do I have a 3 in 3-based number system? No. So like 2, 1, 1. So what is this number though? In decimal. This 2 is not 2. What is this number? Plus this 1 is not 1. You feel it's odd, but it's not odd because you are so used to the decimal number system. All the numbers are just numbers. We just define them as 1, 0, 1, 2, 3. They can be anything. All right. Anything else we haven't converted? That's pretty much everything. All right. Let me see. Yeah, I think that's everything. And next, Boolean algebra, aka logic. Computer logic. Defines the rules in the computer system. So 1 and 1 is no 1 and 1. You don't have 2. 1. You're asking me why? Who defined it? You mean 1 plus 1 is 2. We do have this plus operation in this nature, on this planet. Because if I got $1, another dollar, I put them together, I got $2, I can buy more candies, right? So, but what is and? It's totally designed by human. It's 1 and 1. So what does that mean? We have to find out some really working examples in your life so you can understand what's going on, right? So you can think about this computer logic in this way. Let me write down all the results first. 1 and 0 is 0. And you can swap them, like 0 and 1 is still 0. So that's one of the 2 fundamental logic operators in computer systems, and there are only 2 fundamental ones. So all the other logic are formed by and ors. So and, oh, we haven't done 0. 0 and 0 is 0. So these are all the ands. And computer only has 1, 0, so we're done for this part. 1 or 1 is 1. This is easy to understand. You pick up like 1 or 1, right? Just 1. 1 or 0 is 1. 0 or 1 is 1. 0 or 0, no choice, it's going to be 0. So this is easy to understand. Zero and 0, right? No choice. 0 or 0, no choice. So what about these ones? So I have one example. Think about a basketball game, right? So 1 is a very good player, will lead the team to win the game. And 0 is an awful player, will let the team lose a game, definitely, okay? So 1 is going to win, like Michael Jordan or Kobe Bryant, right? Any of these people. If that person is on the court, that team is going to win, definitely, theoretically, right? Going to win. And 0 is a person like just helping the other team to get goals, right? So their team will lose. If you have 1 and 1, both of the fantastic players on the court for that team, it's going to win. So, for example, 1 is win. So the team is going to win. For this one, you got these two players on the court at the same time. Because this guy is helping other team to win, so you still have to lose the game. Whatever you are doing, this guy is just like helping the other team for every single effort, right? Same for this one. And not mention this one, such a poor team. What about this? They got two good players, definitely win. This, if it's a coach, if you are the coach, you have the choice. You're definitely gonna choose this one, but don't let this one to be on the court, right? So still, you got the chance to win. Same, and no choice. All right, and these are the fundamental ones, and if you can remember these ones, I think, or understand these ones, and I think you are 50% done. um, so if A, sometimes we use letters to represent the digital cases. If A is a case, we don't know if it's 1 or 0, it's just a case, can be 1, can be 0. If A, so and for the operator, and is like a multiplication operator, or is like this, but you are not adding to anything, it's just OR logic. So if A and 1, what you are getting? It depends, right? Depends what is A. If A is helping the other team to win, they can still lose the game. If A is 1, you got two players, you'll win the game. So what is A and 1? Huh? A. Why is A?
If A is 0, then it'll be 0, and if A is 1.
Yeah, so it's always same to A, right? Is that making sense? Everyone? So what is A or 1? Always win, right? Since the coach has a choice. What is A and 0? Just don't let this guy on the court, right? Whenever this guy is there, you have to lose. A or 0. A or 0. It's A since you don't know what is A, but it can be better than 0 at some time, right? So it's going to be A. So what is A and A? A. What is A or A? Double A. Still A. A or A. Still A. Anything else? A and a B. No trap, just AB. It's sometimes we just write it down like this, all right, or a little dot in the middle to represent AND logic. There's nothing similar for the OR logic, but for AND logic, usually we just ignore that little operator here. Okay, great. Let's see if there's anything else. Okay. So what about A naught? So there's another operator, like a bar on the top. So that means not. 1 naught is 0, 0 naught is 1. So A naught is anything inverted to A. It's just A naught, right? If I write down A naught and 1, so what is the result? Yeah, we just treat this one as a black box, right? Yeah, whatever this one is, whenever it's being ANDed with 1, it's still the same thing, still itself. What about A naught and A? Why? Mm-hmm. That's correct. Yeah, yeah, yeah. What about A naught and A naught? Like this one. No difference, right? So if I draw a table, no, I don't want to. Should I draw a table to do that? Let's do it. So AND logic, when 0 is being ANDed with anything, it's going to kill the result. I usually will say that because whenever 0 is being, here's the AND gate as a circuit symbol, it's doing an AND operation. If you got a 0 as an input, one of the inputs, so whatever this guy is, you're getting what? 0. So when 0 is being ANDed with all the other things, you don't even need to look at it. Is that correct? Same for this column. When 0 is being ANDed with anything, you are getting zeros. And when 1 is being ANDed with anything, it's still that thing, still itself. So when 1 is being ANDed with these ones, right, these number logic symbols, you just directly write it down. It's not changing them. Same for this one. So when 1 is being ANDed with these ones, 0, 1, A naught. So you can fill up the table really quickly. I only have 4 left. So A and A is still A. A and A naught is going to be 0. A and A naught, still same thing. A and A naught is 0. A naught and A naught is A naught. So done for the table. Any questions? That's critical, okay? When you're programming a microcontroller, you need to understand what's going on. So first, understand the voltages. Why? Because if your circuit's not working, you know how to debug it. You grab these 2 cables. If you understand voltages and currents, you know where to probe it. We are looking at the electrical engineer in the lab, trying to start debugging the circuit, right? Just grab a multimeter and change to one the appropriate channel, and then start probing. Like, I found this chip is not working, right? How that works? I have to understand voltages and currents. As for analog circuits, but for digital circuits, when you are looking at other people's code, all these makers online, they're designing a little robot or anything else, they already posted their code, Arduino code or other microcontrollers, script for other microcontrollers to the website. Definitely you can directly copy and paste to your IDE and download it to your microcontroller and make it work. But when you're trying to debug it, you have to look at like if they write down something like the example page 4. For example, there's a pin like P1, pin 1. So pin 1 has 8 digital pins for the chip, starting from P10, P11, sorry, P12 until P17. If that's 8 pins, so P1 is 0x. If it starts with 0x, means it's a hex number. FE. So this can show up in the code. You know, you won't be able to understand what is that. You don't even know what is F and E, right? So now you know at least F and E. If you put them together, they are just binary digits. Right? And if you're assigning, so this is an assignment operator. So when you're coding, this is not the equal sign, it's an assignment operator. So it's assigning this number to P1. So P1 represents, so P1 is a register. It has 8 bits, like a memory bank at 8 bits. So whenever you're assigning this hex number to it, you're assigning 8 binary bits to these pins. They are physical pins on the chip. So if you grab a little IC chip, it has all the metal pins. So it's assigning these logic levels to these pins. And what are these logic levels physically? On and off, or voltages. So if you're assigning ones to all these ones, and actually it's backwards. So ones here, 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 and 0 here, like this, right? So all the ones as the other as these digits, but 0 here. So it's pulling these pins up to the power supply. So it's actually, if you have a little LED connected to it, so it's going to shine, right? So turn on the LEDs. So the way the microcontroller or any digital system works is just on off. It turn on and turn off that pin for a different time, a different length of time period for different communication protocols, or just simply just control on and off. So we can have all these fancy digital systems. It's very simple because all the digital systems for their pin, when they're outputting any signals, they don't have any other fancy voltages. If you probe it, they're just like this. Sorry, it's a flat. You know, and that's it. So this is 0 volts. This is the power supply can be 5 volts, can be anything else. But we define the voltage high or logic high as logic 1. So it's all 0 and 1. So 0 volts ground is definitely logic 0, but 5 volts, but logic 1 won't be always 1 volt. For a low voltage computer system, it can be 1 volt sometimes, but for many other ones, they are either 5 volts or 3.3 volts. They are, both very popular power supply voltages. So there are all these things. If you probe it, if you can show the signal on the oscilloscope, use a little probe. This. All right. One more example. A and B is the same as B and A. A and B or C is A and B or A and C. A or B is B or A. All right. Done for Computer Logic 101. You guys did a really good job. So let's look at homework 2, see if there's any potential issues. Oh, yeah, these ones. We haven't done these ones. So if this is a binary number like this, how do we convert it into decimal number? 101.11. What's the decimal number? So definitely 1 here, right? 1 times 2 to the 2 square plus 1 times 2 to 0 plus what? What is this? Yeah. This is how to do it. Why? Because if you have a number 2021.2, if you have a number like 2021.2, this one is actually 2 times 10 to the negative 1, right? Same concept. So this number will be 1 times 2 to the negative 1, so on and so forth. And let's just add them together to get this number. But when you are converting this number back to decimal, no. So this is to decimal. What about from decimal to binary though? 25.4. How to convert into binary? But separately, right? So do 25 first. Is that 25? Let's verify it. What is this? 16. What is this? 8. What is this? 1. It is 25. Okay. So this number equals to 11001 point something. So what is 0.4? How to convert it into binary? So when I'm converting this integer into its binary, I'm trying to shift that point to the left so you can expose every single digit. And now I also want to move that point to somewhere to expose some digits. Since I don't know what is this number, I don't know what it is right now. But the way to shift that point, you can think about definitely not to the left, but to the right, right? So if you want to shift the point to the right, you are actually times 2, not divided by 2. So times 2, or you can say it's divided by a half. It's just times 2. So times 2, you are getting 0.8. And then the way, since there's no remainder, right? It's just times 2, and you are just moving this digit to here. So now it's 0. Nothing to to move. And then times 2 again, 1.6. So this number here, 1. And after you move the 1 to here, you change it to 0. I'm going to explain you why it will work, right? Not just let you know. This is what you want to remember. 0.6 times 2 is what? 1.2, right? And take this one out to here and change it to 0. You can stop. Depends on how precise you want to be. Back or backwards or no, top to bottom, bottom to top. Huh? Why? It's actually top to bottom. 0, 1, 1. Why is that? Yeah, but what if you got a 0 here though? So if you are looking from top to bottom, you have to follow that every time. We have to understand why. So we find out it's actually, for example, we know it's 0, 1, 1, right? 0, 1, 1. Then so for example, we know it's 0, 1, 1, like a binary number. And let's do the same process. So for example, we know this is very close to 0, 1, 1, and this is going to be 0.011, right? So 0.011 is a binary form times 2. What is that? No, times 2. Times 2 is moving. It's moving this digit, this point to the right. And did you see anything here? It's not changing, right? So it's just whatever here is, right? Just move a 0 to here. And then do it again. What's next? 1.1, right? Boom, move it here. Change it to 0. One. Done. Top to bottom, bottom to top. Yeah, you guys are tired. Relax, relax. We're done. After this example, I promise you guys we're done. Okay? Relax. Done. So what's the last question?
Top to bottom.
Top to bottom. Why?
Because why not?
Because top to bottom is 0, 1, 1, and this is 0, 1, 1. Why put 0, 1, 1 here and eventually get 0, 1, 1? Why? Because we know it's 0, 1, 1. How do you know it's 0, 1, 1? I just calculated. I just did it here. So the purpose is to convert into binary. But do we know it? Do we know 0, 1, 1 before we do that? We don't. It shows as 0.4. We don't know it's 0, 1, 1. It equals to 0, 1, 1. So that's why when we write it down here, when we just pull it. When we replace 0.4 with 0.011, it's the same number, and for the calculation, it's 0, 1. It's got it like this. That's how you convert it into its binary. So let me take a final look at this one, so make sure you guys can do the homework. So now you know how to do this part. Since it's recorded, you can watch the video if you forgot. and convert the following decimal numbers to binary. You know how to do it, even for these ones, right? Do you? Convert to decimal, that's the octal number. Think about it. If you have questions, visit my office hour, during my office hours. You can come over here physically. So we don't have office hour on Friday, but we do have office hour on Wednesday. I think I sent an announcement to you guys from Canvas. Or you can make appointments or send me an email. I'm going to reply to our emails, okay? And then convert that number to binary and convert to binary. Oh, we haven't done that. So don't do this one. If you know how to do it, just do it. Otherwise, don't do it. Okay? And you can do these ones, I'm pretty sure. And these ones as well. So A prime means A naught. A prime is A naught. I just tell you, A prime is A naught. Just invert of A. Any questions? I'm sorry, it can be exhausting for you guys. 2 hours. Any questions? It's a long day, it's a long lecture. It's pretty tense, right? All the calculations. You're good? All right, let's call it today. What about that?